We begin Chapter 6 by discussing the concept of the mole. The mole is often described as the chemist's counting unit. So just like a baker might use the dozen, meaning 12, as their counting unit, or a farmer growing wheat might use something like bushels to count the yield of their crop, chemists use the mole to count the amount of reactants and products involved in chemical reactions. However, in the chemistry lab, the most convenient way to measure an amount of substance is by weighing. But the difficulty is that atoms and compounds are very small and typically have a mass at most of a few hundred atomic mass units. And keep in mind that one atomic mass unit is a very small number of grams. So the problem that chemists came up against is that how can we relate the number of objects, the number of atoms, molecules, ions in a sample to its mass in grams? To allow chemists to use practical units of mass to count atoms, the concept of the mole was developed. And what a mole is the number of carbon-12 atoms in exactly 12 grams of carbon-12. Now, it turns out that in that number of carbon-12 atoms, or in 1 mole of carbon-12 atoms, there is 6.022 by 10 to the 23 carbon-12 atoms. So therefore we say that in 1 mole there are 6.022 by 10 to the 23 objects, whatever the object might be. Normally in chemistry it's an atom, molecule, or ion. This number is called Avogadro's number. We normally indicate it as an uppercase N with a subscript uppercase A. So Avogadro's number tells us that there are 6.022 by 10 to the 23 objects in 1 mole of that object. Similar to how there is 12 of an object in 1 dozen of that object. Avogadro's number can be rearranged to give 2 conversion factors. We can say that there are 6.022 by 10 to the 23 objects in 1 mole, or alternatively we can say that in 1 mole there are 6.022 by 10 to the 23 objects. So Avogadro's number basically allows us to convert between moles and the number of objects. A good example of this is if we were to consider how many donuts there are in a 24 box of donuts. Now, the number 24 is a lot smaller than Avogadro's number, so it's not going to be very many moles. So what we need to keep in mind is that there are 6.022 by 10 to the 23 objects, in our case donuts, in 1 mole, and we want to convert the number of objects, which is 24, into moles. So we have 24 objects, so we're going to multiply by the conversion factor that has objects on the bottom line and moles on the top line. And then we're going to grab our numbers from our equivalency, just like we always do when we're doing a conversion. And when I put that into the calculator, I get a very small number, which is exactly what I was expecting, because 24 is a lot smaller than the number of objects in 1 mole. In previous sections, we'd looked at the ratio of the components that were present in a compound. So for example, we might have been given this formula and we would write things like that there are 2 carbon atoms for every 1 molecule of C2H6O. There are 6 hydrogen atoms for every 1 molecule of C2H6O, and there is 1 oxygen atom for every molecule of C2H6O. What we can now say is that if we have 1 mole of this compound, then we would have 2 moles of carbon atoms, 6 moles of hydrogen atoms, and 1 mole, because there's a 1 there that we don't write, of oxygen atoms. And so now we can create what we call mole ratios that express the relative amounts of different components of our compound. And for any one compound, we can normally write many mole ratios. So here's an example that looks familiar. It says in 1.5 moles of caffeine, and then it gives the formula C8H10N4O2, how many moles of carbon, hydrogen, and nitrogen and oxygen atoms are there? So we're starting with 1.5 moles of caffeine in each case, and then we're going to multiply this by the appropriate mole ratio in order to get the moles of the atom that we're interested in. So I know that there are 8 moles of carbon in every 1 mole of caffeine, because I'm just pulling the 8 there from the formula. So in 1.5 moles of caffeine, there would be 1.5 times 8, 12 moles of carbon atoms. And do a similar procedure to calculate the moles of hydrogen atoms in 1.5 moles of caffeine. According to my formula, there are 10 moles of hydrogen atoms for every 1 mole of caffeine. So using this conversion factor, moles of caffeine gets cancelled and moles of hydrogen atoms remains, and this tells me 1.5 times 10 gives me 15 moles of hydrogen atoms, and so on and so forth. The formula is telling me that I get 4 moles of nitrogen atoms for every 1 mole of caffeine. So by multiplying by this conversion factor that I've generated, I'm going to cancel out moles of caffeine, and that's going to leave me with moles of nitrogen atoms. 1.5 times 4 tells me there are 6 moles of nitrogen atoms in every 1.5 moles of caffeine. According to my formula, there are 2 moles of oxygen atoms for every 1 mole of caffeine. So multiplying by this conversion factor, that tells me that there are 1.5 times 2, or 3 moles of oxygen atoms for every 1.5 moles of caffeine. So it's a pretty simple concept and not much of an extension of what we were doing before. Another way that we'll use mole ratios is in the context of a balanced chemical equation. So in this problem, we're told that 3 moles of iron is reacting with O2, and we're asked to calculate how much Fe2O3 is produced. This is often described as a moles of A to moles of B problem. So A is always the compound or element that we're starting with, and B is always what we're ending with. We will know the amount of A, and we're asked to determine the amount of B. And the way to do this is simply to use a mole ratio. So we're beginning with 3 moles of iron, and I should point out that the correct abbreviation for moles is MOL. That's not a typo. And then we want to multiply that by the conversion factor that has moles of Fe on the bottom and the moles of what we're interested in on the top, so that the correct thing cancels out. And then we're just going to put in the coefficients here to generate our correct mole ratio. And there we are, 3 times 2 on 4. It's going to give me 1.5 mole of Fe2O3. So it's a pretty simple process, whether it's a chemical equation or whether it's the formula for a compound. Okay. It's also worth pointing out that N is used consistently to indicate the number of moles of something, and then often people will follow that up with the formula as a subscript to make it clear what it's the number of moles of. You don't always see that symbolism, but it's pretty common. So the procedure that we just followed, taking moles of A and turning it into moles of B, is pretty simple. All we have to do is multiply by the appropriate mole ratio. which will be the coefficient of the thing that the moles is on moles of the thing that we don't know about, over the coefficient of the thing that we do know the moles of. So that's really it. Okay, so let's have a look at this one. It says how many molecules are present in 6.02 mole of C4H10. So 6.02 mole of C4H10, and what I know is that they're an Avogadro's number of molecules in every 1 mole of C4H10. So I've just got to multiply 16.02 by Avogadro's number. So grab my calculator and give that a go. Now it's going to be a very large number of molecules, of course. So here we are, 16.02 times 6.022 by 10 to the 23. And the answer that I got was 9.647 by 10 to the 24 molecules. So that answers the first part of the problem. We now need to answer the second part of the problem. So how many atoms are there in every molecule? Well, you get 4 carbons and you get 10 hydrogens. So you get 14 atoms in 1 molecule. Now, something to point out here is you want to be careful. Don't confuse mole with molecules. They're different things, right? So now, you got 9.647 by 10 to the 24 molecules. And we get 14 atoms for every 1 molecule. So we just got to times our number there by 14. You can times it by 14 over 1, but that's going to be the same as multiplying it by 14. And so then that ends up being 1.351 by 10 to the 26 atoms. So in 16.02 moles of this guy, you get a lot of molecules, and you also get a lot of atoms. Okay, so that concludes section 6.1 about the mole.